Please wait. Okay. Okay. So good afternoon to all. Today we are going to discuss something related to. Okay. Okay. All of you can mention the roll numbers. Okay. Right now in the chat box, just mention your roll number. That will be enough. Fine. So let me present the screen. Okay. My screen is visible to you.
Yes, sir, visible.
Okay. So I think this was our last class discussion basically. Uh, this thing we have started but we couldn't finish, I think. Okay, so I'll just spend some time on this topic, effect of pressure pulse. Then we will discuss some more and more things today, as we are having two periods over here, and will some more discussion will be there regarding the variable area ducts. Okay, so just can you just confirm me, this was our last topic of discussion? Can you confirm, anyone? I think this one was the last topic of discussion, the last class I had.
Yes, sir, it's for the last discussion.
Yeah, but it was not completed, I think, totally, right?
No,
Yes, sir,
sir, it
not
was not
complete.
complete.
Yeah,
It
yeah,
was
yeah. Okay, okay.
until U by C is equals to Mach number. And
Yeah,
what
yeah.
if
That means
Mach
okay.
number is
That means this thing, U by C is equals to Mach number. Okay, that means okay, someone is entering. Okay, so this thing, any velocity divided by the sonic velocity, that ratio, this is denoted by a dimensionless number, that is your Mach number. Okay, and this sonic speed, this thing will now discuss. Okay, so let us just spend some time on this experiment. This is an experiment. Okay, where we can get to know about the concept of pressure pulse, and firstly the conceptually, then obviously mathematically. This is you can see a cylinder piston assembly, and we are having some gas. Say for example, we are having gas, which is a compressible fluid. Okay, and we are pushing this piston in this direction. You can see this arrowhead. You can see this arrowhead. So from the left to right, we are pushing the piston, right? With this, this is the change in velocity. Okay, dv, and here the concept of your wavefront was also discussed, but I will just repeat just for your instance again. So this is the scenario: when the piston moves towards right, it forces the molecules which adheres to it basically, thereby creating a disturbance. Okay, that means whenever I am pushing this piston, okay, on the right side from left to right, and we are having on the right side of the piston, we are having some gas, obviously that movement of the piston will create some disturbance. Okay, that means it will push, there will be some pressure difference, there will be some change in properties. In single line I should say, there will be some change in properties on some region of this medium, whatever we are having on the right side of the piston. Fine. So basically we are getting some disturbance over here, okay, in the form of basically pressure pulse. As we are pressurizing the gas, and gas is compressible, we know, we will get some pressure pulse which will create some disturbance basically. Okay, so if we have now, for just for 1 minute, if you consider, we are not having gas, we are having liquid. What was the condition? If we had liquid, then what will happen? The disturbance, whatever I will create over here, may not compress the medium, because what is the reason? Why it cannot compress? What is the reason? If my medium is liquid, and if I push with the help of this piston, anyone? Hello? Hello? Hello?
yes, sir.
Sir, I think liquid density is more higher than gas, and that is non-compressible.
Liquid density
Yes,
is
sir.
higher.
It's more than gas. Yes, sir.
You should say from the concept of compressibility and incompressibility. Why
Yes, sir.
liquids are not compressible? Liquids are not compressible, I know. Okay, because liquids are incompressible. That means rho, the density, is not changing. Basically, density is constant. Okay,
Yes, sir.
density is constant for liquid because it is my highly compact medium. The distance between the molecules of the liquid is very less compared to gas. Okay, so that's why if we try to compress this liquid, it may not compress the medium due to its low compressibility. I obviously I should not say it is zero compressibility it is having, but very less amount of compressibility this liquid maintains. So that's why it cannot be compressed much. So what will happen to that medium if I push push the medium which is liquid and which is not compressible? What will happen to that medium? It will be responded by all the molecules instantly. That means obviously there will be some disturbance on that medium if I am having liquid over here, but whenever I am pushing it, and whatever the disturbance it is creating by this piston, that will be responded by all the molecules instantly. That means at the same time all the molecules on the right hand side will feel that disturbance, will feel that pressure, I should say. Okay, is that clear, this point? All the molecules, all the liquid
Yes, sir.
molecules will feel that pressure instantly. That means at the same time. But what will happen for the gases? But if I am having gases which is less compact, the disturbance will be felt only by the molecules in the immediate vicinity of the piston. Here it should be written in the immediate vicinity. That means just after this piston there is some region of the gas, and gas molecules are far apart. Okay, we know that intermolecular distance for the gases is much more higher. Fine. So for that, basically what I can say that if I am having gases, the disturbance will be felt only by the molecules in the immediate vicinity of the piston, which then propagates further in a form of pressure pulse. This part is very important. That means whenever I am starting to push this piston, the area or the region just after this piston, say for example some distances, okay, during that distance, during that region, that means just inside that region, the gas molecules will feel that pressure. Okay, not beyond that region. Okay, I am having full gases on the right hand side, but all the gas molecules will not feel that your disturbance. That is the main concept. That is the difference between a compressible fluid and an incompressible fluid, practically, if you think. So what will happen? There will be and we are just pushing, and that means we are go on, just we are if you just go on pushing this piston from left to right, that zone will obviously go towards from left to right, isn't it? That zone, whatever the region I told, that region will also move towards right or not? That region will move towards right whenever I'm pushing this
Yes,
piston. So that is basically known as, that means we are considering, we are just, let us conceive that as a pressure pulse which is moving through this medium with some velocity. Okay, so speed of the pressure pulse is a function of the properties of the gases. That is very obvious, because whenever I'm pushing, so actually this gas or the gases are compressible, so obviously the rho is not constant. So if the rho is not constant, so rho is also related to different properties. Pressure is obviously changing, and if rho is changing, obviously the energy whatever it stores, that will also may change in form of your enthalpy. So different properties of the gas will change, and that velocity, basically that speed of that pressure pulse, will depend on all those properties. Okay, now coming to this wavefront term, though I discussed it earlier, still I am repeating. What is this wavefront? The effect of pressure pulse will be experienced up to a certain distance from the piston wall. That region I was talking about, up to some region. But we have to specify that. How to specify that? With the help of this term, wavefront. So that imaginary boundary is known as your wavefront. Imaginary boundary means up to which my effect of pressure pulse is present or will be felt by the gas molecule. So here let us consider this vertical line. You can see this vertical line, it is written over here wavefront. That means if I push from this piston wall up to this vertical line, this is the region where the gas molecules are experiencing that that pressure pulse or that your disturbance. So this is some arbitrary, basically some imaginary, basically some virtual line, I should say, virtual boundary, I should say, or imaginary boundary, that is basically known as wavefront. So what is the definition? The effect of pressure pulse is felt up to some region or up to some distance. So that basically imaginary boundary up to which the effect of pressure pulse is felt is known as your wavefront. Basically, it is, I told I think in the last class, that this is not a vertical basically line, it is a part of a very large circle, because wavefront obviously there will be some curvature will be present, not a vertical line, but we are considering here as a vertical line as a part of a large circle. Okay, very large circle, say I am having over here, up to which my pressure pulse is present. So but inside this cylinder we are just taking only this vertical line. Okay, this concept of wavefront is clear or not?
Yes, sir. It's
Yes,
clear.
sir.
Okay.
Yes, sir, clear.
And what is happening beyond this wavefront? That means on the right hand side of the wavefront, is there any change of the properties of the gas? Is there any change?
No, sir.
No, because it is not affected basically till now. Till now it is not affected. This right hand side of this wavefront, it is not affected. So I can see from the nomenclature, you can also see P, rho, H. These are some properties of the gases. It is written over here: pressure, density, and the enthalpy. It is written on the right hand side, and which is something different written in the left hand side. That means there is some change. Okay, some increase in pressure, increase in density, whatever, increase in energy, because some entropy is also increasing whenever some movement is present in any gas molecule. Some entropy will also increase. That will basically increase. That is the cause basically of increase in the energy or the other properties of the gases. So there is a change basically on the left hand side of the wavefront and the right hand side of the wavefront. There will be difference in the gas properties. Okay, so this wavefront is the basically the differentiating wall, I should say, up to which I can just differentiate my pressure pulse is present or not. Okay, so the wavefront is propagating. Obviously, whenever I am pushing this piston, this wavefront is propagating through the medium with a relative velocity of c, capital C, which is known as your sonic speed or sonic velocity of that medium. Okay, so this speed
Excuse
of the, yes.
Sir, you are considering this for a particular instant of time.
This whatever the drawing you are having, obviously this is at a, say for t is equals to 1, my wavefront position is over here. Say at t is equals to 2 seconds, so obviously this wavefront will move further on the right hand side. Why? Because my piston is moving. My piston, I'm pushing this. If I don't push, just say I'm pushing the piston, you're just up to this, then at that instant my wavefront will be stand still. Okay, but whenever I'm pushing more, obviously my wavefront will move towards right or not. Is that clear?
Yes, sir. Yes, sir. Clear.
But whatever it is drawn over here, obviously it is at a particular instant. You are correct. Okay, so this is basically the concept of sonic speed. Okay, now I will go to the something mathematical part. Whatever the physical thing you have, the physics you have understood, the physics of the experiment you have understood, that same topic it is continued. So this is the figure that we have already understood. What is the physical significance of this dotted part? Why I have say this is the wavefront, obviously, but when we use this type of dotted type of your nomenclature,
Sir,
you can tell
control
me
volume.
what is the concept of
Control
control
volume,
volume?
sir.
Sir, it is the open channel flow. That is the
No,
thing.
no. What is, if anyone asks me, what do you mean by control volume?
Sir, open system.
No, that is not. Anyone else? That is not the definition of that is not the concept of control volume. What is the difference between volume and control volume?
Sir,
Sir,
whatever my
control
mass flow
volume
rate
means that
entering the system.
Okay, one by
Uh,
one. I cannot hear you. One by one. Yes, someone on. Anyone first time?
sir, control volume means the mass of what water left the volume, or the volume of liquid inside the container will be constant, even if whatever the mass of liquid is leaving the volume,
Hmm.
that equal mass will be also adding from one side. It will
Okay,
be,
that
the
means
volume will be
you
constant.
are taking reference of any particular steady flow, right? You are taking reference
Yes,
for a
yes,
particular steady flow. Yes, steady flow is one example. Any steady flow device, we if you recapitulate the thermodynamics, there if you have seen, I think we have taken the inside volume of any steady flow device as a control volume. Okay.
Yes, sir.
Why? Basically, why? Control volume basically it does not changes its shape and size. Control volume does not change its position basically. Okay, control volume does not change its shape and size and the position, I should say. Any volume, that means mass flow, there is some mass flow in, there is some mass flow out through any device, say for example. But inside that there should be, if there is any region, where that region is not moving or that device is not moving, that means that device is not changing its position, then only I can consider inside that volume as a control volume. This concept is clear or not? This was discussed in the first year,
Yes,
if
sir.
you can recapitulate the control volume, or in the third semester where you have studied the applied thermodynamics. Why we consider, anywhere you cannot consider the control volume concept, where you can consider control volume. This control volume, or here it is not the volume, here it is actually just we are considering as a control surface. So control surface is obviously that boundary is known as your control surface. When I can consider that surface is not moving, that surface is standstill, then only I can consider basically what is control surface. Control surface is basically the boundary of the control volume, nothing else. The boundary of the control volume, that is my control surface. But when I can consider any volume as a control volume, got my point? I can consider any volume as a control
Yes.
volume through any device when that particular region is not changing its position or shape or size. Then only I can, it may be a flow process, that does not matter. There should be mass flow in, there should be mass flow out. But that zone, that particular zone is not changing its shape or your position or size. Then only I can consider that as
Excuse
a,
me, sir.
yes.
Sir, will you consider the cylinder as a control volume?
Yes, that is
Any
my
cylinder?
question, because you see here the cylinder basically, now this is a cylinder, but if I'm just I should consider the gas inside the cylinder. But whenever my piston is moving, whenever my piston is moving, because this cylinder is having some end, there should be some end, say here I am having some end wall, okay, and I'm pushing this piston, right? So in this position, in this that means process, when I'm pushing this piston, can I consider this volume as a control volume? Very good question you have asked. Who have asked this question? Who?
Sir, me, Prishanu.
Okay, so this question is open to all. Say I'm having, there is some end wall over here. This is a very basic concept. Try to understand this. Okay, forget about pressure pulse and whatever we are discussing. This is a very basic concept of thermodynamics. I am pushing this. In this process, practically, is this can I consider as a control volume? Yes, forcefully I can consider that I am coming, because here it is written as a control surface, because I have considered some region as a control volume, that's why. Because this surface I have considered as a control surface. Okay, because volume, if I say left hand side I am having this side I am having some separate volume, and right side of the wave front I am having some separate volume, that is a separate issue. But whenever I am using this term control surface or control volume, that means that is not by definition that should not change its position, isn't it? So practically, is it possible to get any control volume inside this? Any idea? Any idea? Say I'm pushing this piston.
No, sir.
Sir,
If we
when my
change
piston
the
reaches the TDC, top dead center.
Yes, so for top dead center, that is the end. Okay, that is the end of the process. Okay, that is not basically the case of any your that means if I can consider any control, if I just consider any control volume or not, that will not matter much. But whenever this I'm pushing this piston, obviously there is no, if there is some mass flow in, if there is some mass flow out, then I can consider any device. But here I cannot consider either left hand side or right hand side. The volume I cannot consider as a control volume. But if I make some arrangement, then I can consider. But what should be the, always remember what should be the condition for considering any volume as a control volume, because that volume should be, that position of that particular region or the size of that particular region should be constant. That volume should not change basically. Okay, is that clear?
Sir, if we don't move the piston, then we can consider
Then there is no
this.
process basically. If we don't move the
Okay.
piston, is there any question of your pressure pulse, or is there any question of
No, sir.
any
I
disturbance?
am
Yes,
considering the means
basically, but
you
that
are.
basically that type of is any flow process. Okay, we consider that control
Yes, sir.
volume.
I am considering that only.
Okay, okay, but whatever you have told, if anything is stand still, yes, you can just consider that. But the significance of control volume or this control volume term comes when, because there is no difference between then volume and control volume. Okay, so then the control volume terms always we consider whenever I'm having some flow system. Okay, and some particular region of that particular device, if we can consider, if we make some arrangement, or if the device is like such that that particular zone of the volume is not changing its shape, its position, or its size. Okay, but here we are not considering control volume, we are considering as control surface. Then what should be the control surface? Same type of definition. I'm having, say for example, I'm not having any volume, I'm having any surface. So that means this surface should not change its position, right? That means basically by marking this dotted line, I am making this wavefront as a stationary one. I repeat, just by marking this dotted line, what I am doing, what I am trying to do over here, I am trying to make this wavefront as a stationary one, though practically it is not stationary, it is moving. But for my analysis, I'm considering, I'm assuming that this is my stationary. To make it stationary, I have to do some things. Okay, to make it stationary, I have to do something, that I am coming. But what is the significance of this control surface, this wavefront? When I can call it as a control surface? When it is not moving, when it is my stationary. Okay, that means it is in equilibrium. Okay, then only I can say this wavefront is in control surface mode. Okay, otherwise not. So that is basically the concept to analyze. Let us now transform the wavefront into a stationary one. How I can do that? By adding a speed into opposite direction. That means what I told, that this wavefront was moving in which speed? If you recapitulate the last slide, this wavefront was moving in which
dV,
speed?
sir.
Huh?
dV.
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 So basically that speed we called as a sonic speed, right? The relative to the medium, that speed of the wavefront was known as your sonic speed or not. That was from left to right. Okay, that was the sonic speed basically. That is the capital C with which it is moving. Okay, relative to the medium. If you take the relative velocity, okay,
Okay,
with
okay.
respect to this medium, that was C, just last line of the last slide. So if I can apply this amount of same amount of velocity from the opposite side, then I can say this wall or this boundary as a stationary one or not. That means I can say it is in dynamic equilibrium or not. I can say it or not.
Yes, sir.
So because I am applying a same amount of velocity in the opposite direction. That is basically the concept we are doing. Practically we are not doing, we are considering from our end, we are considering how to make it stationary. If we have to make it stationary, what we have to do? We have to apply some equal and opposite velocity. Okay, that is the concept of making this wavefront as a stationary one. So now what is happening on the left hand side and right hand side? If we see from the this, as this was basically there was a disturbance dv, so there will be some difference in the left hand side and the right hand side, because right hand side I don't have any other velocity, I am giving this much of velocity c. Okay, so that's why it is written c over here. But what I am having on the left hand side? In this left hand side I am having this disturbance, the disturbance velocity dv. Okay, so what is the net velocity on the left side of the front? C minus dv. Okay, and on the right hand side, that is my c. So that is basically the difference, because the situation of the gas left hand side, left to the wavefront and right to the wavefront, is obviously not same. This disturbance is present in the left part of the wavefront, but the disturbance is not present on the right part of the wavefront. So that's why there is a change in your velocity, you can see. Okay, so now from the mass balance, if I apply the conservation of mass on these two sides, what I can write? I can write a simple equation rho AC. This is on which side? Rho AC. This is obviously on the right side, isn't it? Isn't it? Rho AC.
Yes, sir. Yes.
Rho AC actually rho 1 A1 V1 is equals to rho 2 A2 V2. That is the basic equation. We all know that. So basically here, as it is a in case of compressible flow, there will be some change here in the rho also. That means in the density also. So in the right hand side, the properties I am having P, rho, and H. On the left hand side, I am having there is some change. Say for example, P plus dP, rho plus d rho, and H plus dH. Okay, these are the changes. Why? Due to the presence of the disturbance, because the disturbance is present up to this wavefront. So that's why on the left side I will be having some change. Okay, so this line is clear because on the left hand side I'm having rho AC. A is the cross section. Okay, cross sectional area
Sir,
of
can you again explain this equation, sir?
okay. Equation is what? If you know the equation rho 1 A1 V1 is equals to rho 2 A2 V2. Okay, the same
Yes, sir.
equation
Yes.
I am using over here. C is the velocity over here. It is not V over here. A is the cross section area. So this is from the mass. Basically, it is also, it can be called mass conservation. This continuity equation is basically coming from mass conservation, mass flow rate conservation. That's why. So rho AC, that is on the right side. Okay, and what is having on the left side? Both the things should be equal because mass should be conserved. Rho plus d rho, that is on the left side. You can see the density. Area is obviously not changing, cross sectional area. And what is this velocity? Velocity here you see, I should write here dv, but by mistake I have written du. Not an issue, you take it as du. Okay, c minus du, that means c minus dv, this velocity. Okay, so whatever the parameters I am having on the left hand side, taking those I have written this. So this is rho AC is on the right part or the right hand side of the wavefront, and this part rho plus d rho into a into c minus du, this is your for the left part of the wavefront. Is this clear?
Yes, sir. Yes. Okay.
Okay, so
Yes,
now
sir.
we will proceed. Very simple calculation are there. Now the mathematics is there. I'm just simplifying. You see, next line I can write rho c is equals to I'm just multiplying. Okay, a will cancel out. You can see here area will cancel out, so you just multiply and you are getting like something like this. Now you can see this last term du into d rho. So you know this is a very small term, so I can neglect this. Du and d rho both are very small term. If we multiply, the this whole term will be much less, so I can neglect this. Okay, so from this I can simplify the equation like this: d rho is equals to rho by c into du. If you simplify, just rho c will again cancel out. So d rho is equals to rho by c into du. Keep it as equation number 1. Okay. Now conservation of mass we have applied. Now conservation of momentum, if we apply in the negative x direction, basically why we are applying, because we have applied this c in the negative x direction. That's why my whole concentration is going on the negative x direction. That's why I'm not changing that. I have kept that negative x direction because the piston is moving in the positive x direction, but we are applying this extra velocity to make this wave front as a control surface. I have applied in negative x direction some velocity, so that's why I am applying the conservation of linear momentum in negative x direction. And what I can get, basically it is something like your from Newton's your second law, basically, because the linear momentum will be conserved in terms of any force. Here you see the change in pressure will create the force, basically minus dp by a. Okay, basically pressure is obviously from left to right, but we are considering this conservation of momentum in negative x direction, so that's why you are getting this minus over here. So minus dp into a, dp is the change in pressure intensity. If you multiply with area, that will give you the change in pressure force. So that force should be equals to m into v2 minus v1, basically change in velocity. Basically, so what is the change in velocity? This is the final, because we are just don't make this mistake, because this is the final and this is the initial. Okay, so v2 c minus du minus of c, this was the initial. So initial, final. I am going from right to left here. So that's why negative x direction. Just consider in negative x direction. So this is the force. Okay, mass flow rate m dot is there over here. You can see into v2 minus v1. That will basically the that will complete the conservation of linear momentum equation. So mass flow rate, again I know it is very simple, rho AC, isn't it? Mass flow rate, rho AV, whatever we called. Here we are not using V, we are using C. So mass flow rate is what? Rho AC. And if you simplify this part, C minus du minus C, I will get minus du. Okay, just by algebra, just by your simplification, I will get minus du. Now this minus will cancel out. What I am getting, A will again cancel out, you can see. So dp is equals to rho c du. Okay, something like this I'm getting from the linear momentum equation. So two things I have to do, conservation of mass and conservation of linear momentum. So dp is equals to rho c du, keep it as equation number 2. Now if we do equation number 2 by equation number 1, what I will get? I will get something, the equation of sonic velocity. You can see, you see, if I do this equation number 2 by equation number 1, should I not get this one? Check it. dp by d rho, left hand side I think it is very clear, 2 by 1, equation 2 by equation 1. So in the left hand side I'm having dp, here I'm having d rho. So dp d rho. If I go for the right hand side, this term divided by this term, you can see rho du will cancel out, rho du will cancel out, and this c I have to take it numerator. So it is my c square. So I am getting a simplified equation, dp d rho is equals to c square, which is nothing but c is equals to under root dp d rho. Now can you recapitulate the last slide that I have told, that this c is basically is an indicator of speed. This dp d rho, this dp d rho is the indicator of sonic speed I told. Can you recapitulate that? Anyone? Hello?
No, sir, actually not remembering this.
Okay. Let me show. So up to this it is clear or not? C is getting, I am getting some equation dp d rho.
Yes, sir.
C
Yes, sir.
under root dp d rho. Very simple. I am just using two things: mass balance and your conservation of linear momentum. That means conservation of mass and the conservation of linear momentum. Two things I have applied. Taking the ratio, I am getting some expression of sonic speed. That is your dp d rho. What is dp? Change in pressure. What is d rho? Change is density. Now whatever I told, let me show you that slide. Just it is this one. Okay, you see over here. Here, whenever I was discussing about the Mach number concept, that del p del rho, okay, del p del rho, I was discussing very greater than u square, okay, for this assumption. Which assumption? For this assumption, for this compressibility will be not substantial, very first class of this compressibility. Compressibility will be not substantial if this is the condition, and from that we have done some mathematical part, and ultimately we got that del p del rho is very greater than u square. Now here we have written that this del p del rho is an indicator of speed, and this term is nothing but c square. There I told you just take a note of this, I will derive this. Now can you recapitulate this part?
Yes, sir. Yes, sir.
Del p del rho, only Alok is responding. Others, what about others? If you are having any doubt, please feel free to ask. Okay. So this is basically del p del rho. Okay, this is basically the indicator of speed that I told there at that point of time. And then we have written that if this left hand side is c square, so u by c, if I take the ratio, then Mach number square is very less than 1. We have written, but we have memorized this one at that point of time. Del p, that means del p del rho is equal to c square. That has been proved over here or not? That has been proved over here or not? C square is equals to del p del rho or dp d rho, whatever. That means differential change in pressure divided by differential change in density. So this is basically the mathematical point of view of the sonic speed. So I think up to this there is no doubt. Okay. So now we'll take help of this, and now we will discuss from this point. We have known this thing, that c is equals to under root dp d rho. Fine. So This is what this quantity basically shows the direct effect of compressibility of the medium. How? dp rho, that means we are giving some pressure and we are experiencing, due to that change in pressure, I will get some change in density. Basically that is the physical significance. If I am applying some pressure in any medium, there will be some dp, because there will be some change in pressure. For that there will be some change in density. Now what will happen for that in different cases? You see, if a system is much compact, then more pressure is required to change the density. Isn't it? The first line is clear to you or not? If a system is much compact, okay, then more pressure is required or not to change the density? This line is understood or not?
Yes, sir.
Sir,
Because
some,
if it
yes,
is
sir.
much compact, then I need more pressure. But if it is a less compact, that means for example gases, okay, I need less pressure, isn't it? So that is basically written over here. If a system is much compact, that means the intermolecular distance is if very less, and the medium is very compact, then more pressure is required to change the density. So that means what? Basically more pressure is required means dp is higher. More pressure is required means what? dp is higher for a small change of density. That means sonic speed will be high or not? c will be high or not for incompressible fluids? Because this compact means it is my incompressible. It is more pressure is required means the compressibility is less. More pressure is required to change in density. That means my obviously my medium or my fluid is my incompressible type of fluid. So for incompressible type of fluid, what will happen to the sonic speed? That means if anyone asks you that the sonic speed is higher for which type of fluid, incompressible fluid or compressible fluid, what should be your answer?
Sir, incompressible fluid.
Incompressible fluid. And why?
Compressible.
Why? This is the reason.
Sir, yes, sir.
This is the reason, because much more pressure is required to get a small change in the density, okay, for incompressible fluid. Because just you think physical, I have to compress more and more because it is not compressible. That property is not there in that medium. So that's why I need more pressure. Okay. So for that I need so that gives me the result that the sonic speed is much more high. So this can be also compared from the analogy of the solid mechanics, that compressible fluids are like elastic body. The same concept you can consider, that for the compressible fluids are like elastic body. Okay, so elastic body is having the property that it can just easily compressed, or it can just your elastically just it can deform. That is the concept from the solid mechanics we have. So compressible fluids acts like elastic body because dp rho refers to the elastic property of the medium, because there small pressure change is required for the change in density. Okay, so compressible fluids are like elastic body, incompressible fluids are like inelastic body, I should say. Okay. Now, from the thermodynamic point of view, most of the compressible flow process will be isentropic. This term is very important in almost, you can say, all the cases. All the cases, my flow, I will consider that isentropic flow. Okay, isentropic flow means the flow is my reversible and adiabatic. Though
Entropy will
practically
remain
reversible
constant.
is not possible. Yes.
Entropy will remain constant. Isentropy.
Yes, isentropic means entropy is constant. Okay, so isentropic process means the process should be reversible as well as adiabatic. That we know from the thermodynamic point of view. Okay, so for ideal gas, what we can write, we know very basic equation: P by rho to the power gamma is equals to constant. For any adiabatic process, we know that. So if I modify this, if I take log or log E base or ln, uh, your ln p minus of gamma ln rho is equals to ln constant. Okay, I can write from this equation. Okay. So if I differentiate now, what I will get, dp by p minus of gamma into d rho by rho is equals to 0, because this term obviously it is my constant. So if I just differentiate, if I give derivative, obviously I will get 0 on the right hand side. Okay, so this thing I know, c is equals to dp d rho. Okay, so how I can rewrite this part? How I can rewrite for ideal gas, that means for isentropic processes, c is equals to this dp d rho. Now you see, if I take this dp by p on the left side and this gamma d rho by rho on the right side, I can generate this dp d rho term. Okay, dp d rho term, and that is nothing but gamma p by rho. This p will be on the numerator, so gamma p by rho. So that's why we are replacing this dp d rho term from this equation, and we are writing c is equals to gamma p by rho. And we also know from the equation of state that p by rho is equals to rt. Okay, pv is equals to rt, we know. So that is basically the specific volume. If I take, that means this is 1 by rho. So p by rho is equals to rt. Now this p by rho is equals to rt. If I replace over here, what is the modified equation of c? I am getting c is equals to under root gamma t. So c is equals to dp d rho under root dp d rho is the general equation. Okay, I repeat, c is equals to under root dp d rho is the general equation that is applicable for any process, that is applicable for any flow process. But if my flow is isentropic flow, what will be the expression of c? This is the expression of c. C is equals to under root gamma rt. Up to this clear or not? Up to
আবার
this
একটু
clear?
রিপিট করুন।
Clear, clear.
কি বললি উদ্দেশ, কিছু বলছিলি?
স্যার ওই সি এর ওটা রিপিট করুন না।
আচ্ছা, লাস্ট যেটা বললাম,
হ্যাঁ হ্যাঁ স্যার।
acha like c in general, this is the equation. My point is very simple. C is under root dp d rho. Sonic speed is under root dp d rho for any medium, for any process. Okay, but whenever I am calling the process, whenever I am specifying that flow process is my isentropy, that means reversible and adiabatic, because in most of the cases, in case of nozzle, I will consider that is my your isentropic flow. So in that isentropic flow, if these are the parts that I have calculated right now and I have modified that equation, c is equals to under root gamma rt. Okay, so this c is equals to under root gamma rt, this is valid for isentropic flow process, and c is equals to under root dp d rho, it is valid for, this is valid for any process. Because then if my process is not isentropic, that means if my process is not adiabatic, then obviously this is not valid. P by rho to the power gamma is constant is not valid. There may be some other equation. According to that, I will get some other type of ratio. Okay, other type of expression I will get for this dp d rho. Then obviously the equation may change, but this is the in general equation. C is equals to under root dp d rho, and for isentropic flow, keep this in your mind that it is under root gamma rt. Now it's clear?
ক্লিয়ার।
Okay, thank you. So next I will discuss the stagnation properties in a fluid. Okay, so it's 3 p.m. or not? It's 3 p.m. right? So I'm giving you
Yes.
5 to 7 minutes break. Again join in the same link. Okay, again join in the same link. We are going to discuss stagnation properties. Okay, some mathematics are there, and up to this I will discuss today isentropic flow through variable area duct. Okay, very important. So some mathematical parts will come gradually. Okay, that will be required for your problem solving also. Up to this, is there any doubt?
No, sir.
Okay, thank you.
No,
Then
sir.
see you after 5 minutes. All of you join
Okay.
after 5 minutes. Okay,
So 3-5 we will join.
3-5. Okay, fine.
Okay.
Okay, 5 minutes.